Welcome students. In today's class we'll study reflection on the basis of wave theory. Now in this topic we will derive the laws of reflection on the basis of Huygen's wave theory of light. Okay, so first we will explain the first law of reflection on the basis of Huygen's wave theory. Now consider a reflecting surface xy. Fine. Now on this surface a plane wavefront AB is incident. This wavefront is moving in this direction. The wavefront AB interacts the reflecting surface at point B and gradually it interacts towards the point C. Now, according to Huygen's principle, each point on the surface BC will act as a source for secondary wavelets. Now, each wavelet will start growing at a velocity c. Now, during the time when the disturbance reaches from point A to C, during this time, what happens? The disturbance from point B will reach to the point D. Okay, or we can also say it like this: during the time when the disturbance reaches from point A to C, a secondary wavelet from the point B will start spreading. Fine. Now it has started spreading like this. So what happens? It will spread at a radius of how much? This will spread, this is the radius. This will spread at the radius of c times t. What is c? C is the velocity of light. The velocity by which this point is moving towards point C. And what is t? T is the time taken by the point A to reach to point C. Now we know when we write c, your velocity, and t, your time together, it gives us the distance. This distance is the radius of the circle. Fine. Okay. So in this manner your wavefront gets reflected. Therefore I can say your surface CD is the reflected wavefront. Fine. In this similar manner, what happens? As the point A moves towards the surface, the one which are already reflected starts moving towards point D. Fine. Now in this case you can see the, let us say this is 3/4 part. Okay, this is 1/4 part. So what happens? The 3/4 part of the wavefront is moving towards your wave, whereas 1/4 is moving towards the point D. Fine. Now as gradually it keeps on moving, so it moves like this. Now in this case what happens? The half of the wavefront, this half, is moving towards point C, whereas the other half which has already been reflected, it moves towards point D. So what gradually happens is that all the points get reflected. So you might see something like this. And when finally the point A reaches to your point C, your final wavefront will look something like this. This CD is your reflected wavefront, whereas your AB is the incident wavefront. Fine. If you have any confusion, please don't hesitate to ask. I will re-explain it to you again. Now, consider your triangle ABC and your triangle DBC. Fine. In this triangle, consider this angle. This angle will be 90 degree. Why? Because we know the wavefront, this wavefront AB is always perpendicular to its direction of propagation. Fine. So therefore this angle will be 90 degree. Whereas in your triangle BDC, consider this angle. This angle will also be how much? 90 degree. Again, using the same principle. The wavefront is perpendicular to the direction of propagation. So I have written angle BAC equals to angle CDPY because both of them equals to 90 degree each. Now consider your side BC. This side is common to your triangle ABC and your triangle BDC. Fine. So these two, or I can say this side BC will be equal from both the triangles. So BC equals to BC because they are common. In triangle ABC, this distance is how much? This distance equals to c times t. C is the velocity of light, t is the time taken to move from A to C. Fine. So this distance equals to ct. Similarly, in triangle BDC, this side BD is also equals to CT. C is again the speed at which the light travels and T is the time taken for B to reach to the point D. So I can write AC equals to BD because both of them equals to CT. Therefore, by the property of SAS, I can say triangle ABC and triangle TBC are congruent to each other. If they are congruent to each other, by the property of CPCT or your principle of congruence of triangle, I can say angle ABC equals to angle DCB. I can say angle ABC, this angle equals to angle DCB, this angle. So this is angle is my I and this angle is my R. Therefore I equals to R, angle of incidence equals to angle of reflection. Therefore we have proved the first law of reflection. Coming to our second law of reflection, further the incident ray SB is perpendicular to the incident wavefront AB. My incident ray SB is perpendicular to my incident wavefront AB. Normal BN perpendicular to the reflecting surface xy, normal Bn perpendicular to the reflecting surface xy, reflected ray Bd perpendicular to the reflected wavefront CD. My reflected ray BD perpendicular to the reflected wavefront CD. Now if this is the plane of the paper, if they are perpendicular to the plane of the paper, that means they all lie on the paper, isn't it? If they all lie on this paper, therefore I have proved my second law of reflection. What does this say? The incident wavefront or your incident ray, the reflected wavefront or your reflected ray, and the normal all lie on the same plane. This is the same plane. Fine. Okay. So that's it for today's class. Thank you. If you have any confusion, please don't hesitate to ask. I will re-explain it to you again.